for last two lectures we are talking about how to design while respecting the fact that there is uncertainty in the system. And in that context, we talked about primarily two types of schemes. One is the reliability based design optimization, where you try to design while ensuring that there is a minimum level of reliability that the system always has. And how do you ensure that? You put the reliability as a constraint in your optimization problem. So there is a probabilistic constraint, a reliability constraint, and then there is a deterministic or probabilistic optimization function, objective function, and you try to minimize or maximize it based on the problem at hand while satisfying the reliability constraint that you have defined for the problem. And this is what RBDO is all about in a broader sense. The second thing that we discussed about is robust design optimization, where the idea is that you want to minimize the propagation of uncertainty from the input to the output, from the design variable to the objective function, while satisfying certain constraints. And in robust design optimization, there are different point of views, and that arises from what robustness means. So the way we are defining robustness is that your input perturbation should not be, or the perturbation in the input, the propagation of that should be minimized when you reach the output. Any perturbation in the design variable should not propagate to the cost function or the objective function, or any perturbation in the input variable, the propagation of that to the cost function or objective function should be as less as possible, while satisfying some probabilistic constraints, and these probabilistic constraints are not necessarily reliability constraint. The probabilistic constraints are in terms of the statistics of the constraint, because your constraint is also a random variable, so you will look at the worst case scenario there, mean plus standard deviation, and that should not exceed certain threshold, and that is how you will proceed. And this is one point of view, and this is the point of view that we are primarily focusing on. But there is the other point of view where you solve a max min kind of problem or min max kind of problem, where you take the maximum response and try to minimize that. The idea is that that will be probably more safe, whereas, and that's one way of looking into robustness, right? That it will not fail. Even if there is perturbation, it will not fail because you are minimizing the worst case scenario. But that I believe will be more costly. That will be more costly, right? So yeah, so that is another way of looking into robust design optimization. Money, financially. No, actual. So whatever design variable you will get, that will give a. So suppose you get some width and breadth, let's say. So you will get a conservative. So that means it will be more costly in that sense. Actual cost, not computational cost, right? And that is kind of obvious because you are minimizing or working with the worst case scenario, right? Okay. So this is what we have discussed primarily. Coming to the challenges, we discussed that computational cost is the primary challenge. And today we'll focus on how to solve a robust design optimization problem, or rather it's an optimization problem, so I'll not go into the optimization part of things, but I'll focus on things that are specific to robust design optimization. For example, computing gradient of the statistics, which is not there in a usual optimization problem. Computing gradient is there, the optimization algorithm will not change, but computing gradient of the statistics is something that is very specific to robust design optimization, so we'll talk about that. And then there is this double loop, nested loop kind of thing, right? So we'll see that how it can be made into a single loop, right? And we'll look into two things or two ways of making it or converting it into single loop. One is the based on Taylor series. The other one is based on stochastic or surrogate model for stochastic simulator. Okay, or surrogate modeling in general, right? With that background, let us start. Okay, so to quickly recap, what was the problem statement in RDO? If you remember, we are looking at D star. So we are trying to find out the design variable that will give me the optimal, that is optimal, and you get it by minimizing D for some cost function, but that cost function in a deterministic sense was deterministic, but now it is probabilistic. So your cost function, one of the ways that you write it as alpha times mu of the usual cost function, mean of the deterministic cost function, plus 1 minus alpha times standard deviation of the deterministic, of the cost function that you consider in the deterministic case. The cost function is no longer deterministic. That's why mean and standard deviation is coming into picture. But if it was deterministic design optimization, that C would have been the cost function, and that would have been deterministic, right? And this C is function of D and X. I'm not writing it here. We wrote it last 2 lectures. C is function of D and X. D is my design variable. X is the random variable. D can also be random, but for now let's consider D to be deterministic, right? And we'll go like that. Actually, D, even if D is random, in that case you design for mean of D, and that is constant or deterministic, right? So in that sense, so we'll try to find out mu of D in that case. Okay. Subjective to, there will be some constraints. So what are the constraints? Remind me. In the usual case, maybe the constraint was Hx should be less than equal to some threshold. In this case, what will it be? Mu of H plus 3 times or k times sigma of that should be less than equal to that threshold, right? Subject to mu of H plus k of sigma of H less than equal to 0. I am assuming that the constraint was written in a form that H is less than equal to 0. If it was H less than equal to H threshold, take H threshold to the other side, it becomes less than equal to 0, no big deal, right? And then what is the other thing there? That is the bounds of the design variable. And so D lower limit less than equal to D less than equal to D upper limit. This is the problem statement that we solve in robust design optimization. And this is the problem statement that you have seen in the last lecture, nothing new, right? So now the question is, how do you solve it in practice, right? It's a constrained optimization problem. All of us agree on that. There are constraints, so it's a constrained optimization problem, right? Because it's a constrained optimization problem, like any other optimization scheme, you will use the Lagrange multiplier to convert this constrained optimization into an unconstrained one, right? So what you will do is you will convert it into unconstrained one. The unconstrained variant will be D star is equal to arg min over D mu of alpha of mu c plus 1 minus alpha of sigma c. This is your objective function plus lambda times mu h plus k sigma h, right? And maybe I should put another bracket here. Let's make it like this and make it like this. That is, the minimization is now over the modified cost function, a cost function that includes the Lagrangian. Subject to, the limits will be there still. d upper limit, d lower limit will still be there, but I am not writing that. So it basically converts, as you are aware of this already, and constraint optimization into an unconstrained optimization problem. The lambda needs to be found out. I mean, it becomes another of your design variable, and you try to find it out, right? Okay. So you are aware of this, right? So now I need to solve it. What will I do? I will have to take the gradient, right? Assuming I am using some gradient based scheme. You are not forced to use gradient based scheme, but that is the preferred one, that is the most efficient one. Gradient free are very expensive because they are more like greedy sampling kind of thing. That is what you do. And also you sometimes inspire it based on biology, crossover, mutation and all those things. But generally our choice is to go towards gradient based. And in gradient based, which gradients do we need? We will have to compute the gradient of this term that is inside the argmin, I mean that bracket. We will have to compute the gradient because that is the cost function. In other words, if I look at the left hand side, I will have to compute gradient of the cost function and gradient of the constant. Correct? That is what I have to compute. Now look closely into the cost function and the constant. In both cases, the cost function and the constant both are additive in nature. Mu plus sigma, mu plus sigma. Yeah, there are some factors, but those are constant. So both constraint and objective function are additive in nature, which means when you will try to take the gradient of that, you will take the gradient of these terms individually. You will take the gradient of the mean and you will need to take the gradient of the variance or standard deviation. You will be taking those gradients independently and then summing them up. You agree with that? Because ddx of a plus b is equal to ddx of a plus ddx of b. So that exact thing you can apply here, the additive rule, right? And you can do that. So if you are with me on this, then you will also agree then that, so now then we should only discuss how to compute gradient of the statistics, or rather the first two moments. Because if I can compute the gradient of the first two moments, I am in a position to compute the gradient of the objective function and of the constraint, which is equivalent to computing the gradient of the unconstrained optimization objective function, which means I am now in a position to use any of the standard gradient based algorithm, be it Newton's method, be it gradient descent, any of this, right, to solve this problem and find out d, right? So the primary challenge is finding out the gradient of the moments, right? Okay. So to solve this problem, using gradient based optimizer, here we need to compute the gradient of the moment or first two moments, right? Although writing moments, it's actually first two moment, and that you are kind of aware of by looking at this expression, right? So let us go step by step. Let us first take the first moment, the mean, and let us see how we can compute it, right? Alpha 1 minus alpha k, I don't care about, those are constant, so I will not go there. Okay, so the first thing is gradient of the first moment, which is my mu c, let's say, right? Now, if I can compute gradient of mu c, I can also compute gradient of mu h, because so in a generic sense I need a scheme for computing gradient of the mean. It has nothing to do with whether it is the mean of the cost function or mean of the constraint. I just need a scheme that will allow me to compute gradient of mean. That's all I need, right? So I will only work with, let's say, mu c, but you will see that you can easily extend it to mu h as well, right? So what are you interested in? We are interested in computing gradient with respect to d of mu c, right? Now, which is equal to gradient with respect to d. What is mu c? Let's say you are computing it based on some sampling. Mu c is expectation, right? How do you represent it? Either as an integral, or in our case, in most cases, as a summation. So you will draw samples from x randomly, and that's how we will represent it. So it will be 1 by n summation I equal to 1 to n ci, or c of, let's say, because the d we for now are considering to be deterministic, right? So d comma xi, right? So it also changes with d, but for a given d it's a function of d, but x is random. So basically I will draw samples of x and do it. If d was random, there is no problem, that I will then try to calculate gradient with respect to mu of d, and then mu of d will go inside, and that will become a constant. So that will not matter, right? And then mu of d plus some perturbation. What will I do? So suppose d is random, right? I'll write d as some constant term plus some probabilistic term. So then I will write c as a function of d, comma, or d put a deterministic term, d tilde comma x. And then this I will call as my new x, this I will call as my d, and you go back. So we will just sample from here, right? So that's what I can always do. So this scheme is generic, it will not matter. So you can always write it like that. Yes, the new x. Okay, the new x, it will get into that. Okay, it's a multivariate kind of thing, so it will be there. We will only know the d mean, d standard deviation will know something, and we should know the distribution of d in that case. Otherwise, we will not be able to go ahead. So you are trying to find out the mean of d, optimize for mean of d, but you are aware of what is the standard deviation and what is the distribution of d. So for example, you are aware that because of manufacturing error, what will be the distribution? Because d is manufacturing uncertainty. So what is the distribution? You are aware of that. You can assume that the manufacturing uncertainty is because of n number of factors, where n is very large, they are IID, so it's Gaussian. Done. You can assume that d will never be negative, so it's log normal. So those kind of information you will need, or assumption you will need, but this can be done, right? Okay. So that's why I'm not going there. You can always convert that. This is enough. What I'm doing is actually enough. Anything can be converted into this form. Okay. So yeah, so this is not something that we are going to discuss, or rather we already discussed it. So to motivate why we are focusing on this.
In X also we will have the mean and
we will have, but x is not in the design variable, so I don't need gradient with respect to x. So I don't care about that. Why I'm doing it like that, because I will need the gradient with respect to d. So that's why, right? Okay, this is fine. Now what will happen to the gradient if you have this form? Will the gradient not go inside the summation? It will, right? That is a property of gradient, that gradient of sum is equal to sum of gradient. So the gradient will directly go inside the summation. So what will you be left with? 1 by n summation I equal to 1 to end gradient with respect to dc, right? And what is this quantity now? It is expectation of the gradient of c, right? It is expectation of the gradient of c. So gradient of expectation of c is equal to expectation of the gradient of the c. The gradient and expectation can always switch places because expectation is a linear operator. It is happening because expectation is a linear operator, and that is why you can get away by exchanging them. With linear operator, you can always exchange gradient and the linear operator, right? So this is equal to expectation. This was also expectation by the mu c of gradient of c. C is function of d and x, and the expectation is with respect to x. Which one? dj you are saying? No, d is not changing. I'm telling you why. D is changing, but in this case it is not changing. Think of an optimizer. When you stochastic gradient descent, I think is the easiest one to understand. What do? D star or di plus 1 is equal to di minus some lambda times gradient of the cost function evaluated at a given d. So for a given step, optimization step, the d is constant. The d is changing when you are looking over all the optimization steps. This is for a given optimization step, and you are looking at the uncertainty because of the uncertainty in the system, not at the statistics during the optimization. The statistics is because of the randomness in x or even d, but not because of the statistics does not represent how the optimizer statistics, right? So that is why d is constant, because it's like a given step. To be more specific, when write grad of d is equal to di xj, but the summation is over j, because that means it is at the ith step. That you can do. But there is a nested loop. I'm only looking at computing the gradient, because for each iteration you need to compute it. Okay, this is fine. So this was easy, right? Variance or standard deviation is not that easy, because that is no longer a linear operator, right? So let us look into that, what will happen. So let us move ahead and look at the gradient of this second moment. Now I will remind you at this stage that remember that at the beginning I said that different books has different definition of second moment, although they are same. Some will say that expectation of x square is the second moment, some will say variance, some will say standard deviation, but they are related. So in this case I am saying standard deviation to be the second moment. Ideally second moment should be variance, not standard deviation, because the unit, right? But that's okay. So gradient of sigma, I'll say gradient of the second moment. The second moment, right? So we'll go ahead with that. I was thinking of something, but I forgot. I'll come back to that. Okay, if I remember. So gradient of the second moment. What is the second moment? We'll start with variance. Why variance? Because I don't want to deal with a square root. So variance will not have the square root. So that's why. Okay. So let's start with variance. So variance of C, right? D comma x. Variance is with respect to x. Keep that in mind. That variance is with respect to the random variable, not the design variable. Unless and until the design variable is also random, obviously. But in that case, our design variable is main. So then it's not random. So variance of C D comma x, right? Now, what should I do? I want the gradient of that, obviously, but you can understand that the easiest way to approach it is to convert it into a expectation. So I will write it in form of expectation. There are two ways of writing it: expectation of x minus mu whole square. Another one is expectation of x square minus mu square. Which one will I use? The second one. The second one decouples the two terms. Expectation of, because otherwise expectation of x minus mu whole square, I will not like that, like to use that, right? So rather I will like to use expectation of x square minus mu square. So this is equal to expectation of c square, so c square d comma x minus mu square, right? So maybe mu c square is, what should I write? Right? Let me write one more sentence. So this expectation I can write it in a summation form, assuming n samples. So what will it look like? 1 by n summation I equal to 1 to n c square d comma xi minus mu c square, right? Now I have this 1 by n summation form. Now I will take the gradient, right? Because you can understand that the gradient I will push inside the summation. Okay, although it will not work directly like before, but I can do that, right? So variance is equal to sigma square. So first left hand side will become 2 sigma multiplied by del gradient of sigma, right? So taking derivative with respect to d. So gradient of d of variance with respect to x of c d comma x, I hope I wrote it correctly, yes, is equal to gradient of d of sigma square, which is 2 sigma multiplied by gradient of d with respect to sigma of c, right? Sigma square 2 sigma multiplied by del sigma del d, correct? So this is my left hand side. Let us move on to the right hand side. So until this point it was only left hand side, I did not even look into the right hand side. So right hand side I will take gradient. So the first term will be gradient of 1 by n summation c square d comma xi. Let us put the or push the gradient inside. What will I get? 1 by n summation gradient of c square, which is 2c gradient of c. I will go with that. So it is equal to 1 by n summation I equal to 1 to n. So there is a c square sitting there, which will become 2c. So 2 I am bringing outside, okay. So c, and c is function of d and xi multiplied by gradient of c. Yeah, c, and c is obviously function of, evaluated at d comma xi, right? Everyone follows what I have done?
Second sigma, 2 sigmas.
Which one?
Second, 2 sigmas.
Why 2 sigma?
Substance.
I am confused. What you were saying? Oh, the outside one, right? Oh yeah, obviously, correct. Oh, the outside one. I was looking here. Where is sigma? Yeah, it's obviously, right? Correct. Thank you. This is fine. But this is not complete because there is a mu square sitting there. So mu c square, I want to take gradient with respect to d. What will I get? Minus 2 mu c gradient of mu c, right? Which I have already computed, by the way. Exactly. Minus 2 mu c multiplied by gradient with respect to d of mu c. And this is not constant, we know that from here. This is something we have already computed, right? So this is something we have already computed, right? So the 2 will cancel out, left side, left hand, right hand side. So which implies sigma c gradient of d sigma c is equal to, what is the first term? Expectation of c times gradient of c. 1 by n summation of the term, right? The term is c times the gradient of c. So first term is actually expectation. Expectation of a non-trivial quantity, but it's an expectation nonetheless. Expectation of with respect to x of c d comma x multiplied by gradient with respect to d of c d comma x. It's like expectation of a times b, I mean, whatever you get, right? Correct? It is fine. Minus mu c. So this is expectation obviously, and gradient of mu c. So which will be equal to expectation. So mu c I am writing intentionally of c d comma x. This is mu c. Mu c by definition is this one. I was just not writing it. And the second term will be multiplied by expectation with respect to x of gradient right? Any doubt? So now, if there is no doubt, please note it down, then I'll go ahead. So this is one of the expression I got. And this is the other expression I got, right? What are the importance of this of this expression? These two red blocks, right? What do you think is the importance? The importance is that you can just compute gradient as usual and use those gradients to compute the overall gradient by taking expectation and variance and all you need to do is calculate c and gradient of c for each of the samples. And then by using those you can find out what you originally intended to find. Which means computing gradient, you don't need to worry about computing the gradient of the statistics. You just compute the gradient and evaluate obviously the samples, and using those just plug and play into these two red boxes, and that will give you the gradients that are needed for you to, or that are needed by your optimization algorithm, right? So which means in your code, when you write an RDO thing with gradient base, these are the things you are supposed to use. Okay, instead of using some numerical, there is no point using some numerical solvers, because then you have to perturb many times, because for each d you have to find out the mean, which means you have to do a sampling and then perturb that d again, find out the mean, find the change in the mean, divided by the step size. That is what finite difference you have to do, if you have to do. which is impossible. Because at each point you are finding out statistics. So let's say 1 million sample, perturbing again 1 million samples, difference, and then you are doing it. Whereas this one will directly give you direct. I mean, you just need to sample once, not twice, and all those things, right? And you don't need any finite difference. Exactly, exactly. So, and it also shows that back propagation can be used here. I mean, if you build a deep learning kind of thing, there is the computation graph holds. So you can also compute it using the back propagation kind of thing. You don't need to, it's not that difficult. I mean, it looks like how do you compute gradient of the statistics? No, it's simple. It's not difficult, right? Okay. Many people do that actually in generative model, right? You need to compute the gradient of the mean, and this is what is happening in some sense at the back end that you are probably not you knowing, but back propagation is doing that. Because back propagation will track your calculation thing, right, and then propagate through that. And this is what how you are calculating. Okay. So you can compute it. The main message is that you can compute it using this gradient and the samples. That's all, or samples and sample gradient. That's the correct terminology, right? Okay. Okay. So this addresses one concern that I wanted to address. The other concern is it's still nested. This is for a given D. So for a given D, you need to sample X. As the D changes, you will again sample X. Expensive, right? Because this will have to be computed at each iteration step. That makes it expensive. Can we make it simpler in some way? But before going there, keep in mind that this same thing will be used for both mean and both cost function and constraint. I mean, that I'm not repeating, but I already told you. But let me repeat that this same kind of thing will, I mean, obviously this is nothing special with cost function. The mean and standard deviation formula is all we are using. So this will also be used in mu h and sigma h gradients, right? The bound will be handled, the bound means the last one, right? That will be tackled by the optimization algorithm. So I'm not going there. So that the optimizer will take care of. The idea is that you will provide a gradient to the optimizer will do the rest. Because it's not an optimization course, I'm not going there. But their optimization algorithms have their own way of handling bounds.
In the nested loop, we can provide D from that range to that range only.
Of what? Of what?
Of D value.
You cannot. Because this distribution of D values it will take, you don't know. For computing expectation, you need the distribution. And D is, even if D has distribution, it's at a given D. But during the optimizer, what points it will take, you don't know. What step. So that is not known. But we will do something like what you are saying now. Okay. So the second issue is that it's still nested. So let us try to address that. RDO is nested, right? So what can we do about that? The easiest way of handling is, it is what he was just now suggesting, but with a Taylor series, right? So let us look into C. You can use the same thing to H as well. So look at C. So what is my C? C is a function of D comma X. X is my random variable. So I know the mean of the random variable, I know the statistics of the random variable, I know the distribution of the random variable. D is like deterministic. So D I will not touch, but D will vary, D can vary during the optimization step. So this, if I write it in Taylor series, considering D to be constant and only X to be varying, because Taylor series you vary one variable, right, at least. So I will write it as C at D comma mu X, right, plus gradient of f with respect to x, not d. So now x is coming in the gradient term. So gradient with respect to x of c, in this case f, which is c, and evaluated at d comma mu x, and this will be a vector, right? So let's write a transpose multiplied by x minus, and the higher order terms I will ignore, right? So this will work if it is not highly nonlinear and all of those things, right? Now I will take the, what do I need? Expectation and variance. Let's take the expectation. Expectation of left hand side, what will I get? And expectation is with respect to x. Keep that in mind. Let me write it. The first term will be, I'll take the expectation, right? And that's a constant. So it will be c d comma mu x. And the second term expectation will be, the gradient is a constant, but x minus mu x, expectation of x minus mu x is equal to, it will be 0. So the second term is 0. I will not write it. You have seen it in form. Let's take the second moment, variance. The first term variance is, variance of c d comma mu x is 0. That's a constant. Variance of constant is 0. And for the second term it is, you can write it directly. We did it for Gaussian. For the form part, there was a typo and mistake that I made in the class, but this is what we are computing, right? What will it be? Gradient c, this is a constant, right? What is variance of ax? A transpose variance of x times a. I mean a square variance of x or a transpose variance of x a. Same thing should happen here. So this is the constant. So transpose multiplied by variance of x. Variance of x is, you are aware of that by the variance of x, because that's your random variable. Like the mean is you are aware of, variance also you are aware of. Let's take the covariance matrix, so sigma of x multiplied by same thing, variance of ax is equal to a square variance of x. So instead of that, when it is a matrix vector form, a transpose variance of x, this thing, right? So if you assume it to be linear, this is what you can get, correct? And this thing, when you write in the summation form, will give you the exacting like form, right? If you write it in summation form, it will give like that. But anyways, we're not going that. Obviously in form the sigma will not be there because that was what deterministic. So this is fine. Now why is it helpful? It is helpful because now imagine during computing the d, right, through the optimizer, the mean of x, will it change? It won't change because x is a random variable that does not change with iteration. So mu of x is constant through the optimization process. Sigma of x is constant throughout the optimization process, which means this mean and standard variance or standard deviation, if you took a square root, at each optimization step, all you need to do is plug in your value of d at that step. You just take the value of d, whatever you got at that step, plug it in here, and that will give you the mean and variance without any simulation. Because it is now no longer a function of x, it's a function of mu x and sigma x, which are known to you, which are the statistics. So mu x and sigma x is known to you. The gradient, I'm assuming, is known to you, but the gradient is also constant. you will have an expression of gradient which is function of d and mu x. Mu x does not change. So at each iteration, the d value you plug in into the gradient, you will get a gradient at that step. And that's your variance. Mean is even simpler. You just evaluate C at the new design point and mu x is constant, which means it's a single loop now. Once you have done this Taylor series business, all you need to do is two straightforward evaluation, closed form. And now if you want to take gradient, the previous gradient you don't even need, just take gradient directly. You don't. Obviously, that will always have. For a random variable, why are you even calling it a random variable? First, because it's not deterministic. Second, because you know the PDF of that. You know the PDF means you know the statistics. If you know the statistics, it means that you know the process. This is only valid when your cost function is weakly linear or almost linear. That's when, right? So, because d anyways I'm taking constant, so I'm not expanding about d. So d is not a problem. X is a problem. If it is highly nonlinear in x, then you are screwed. You cannot use it. Obviously. So that's the linear thing, right? So that's exactly. So obviously that's why it is not popular. That's why I've been saying for 2 lectures it's nested is expensive. If it was so exact, I will never claim it is expensive. I'll say it's similar as normal optimization. I'm not doing that, right? So this is an approximation. In some problems it will work, in most problems it will not work. Because even if your cost function is linear, just for the sake of argument, you also have the constraint to deal with, and that might be highly nonlinear. Cost function may be simple, right? But your constraint is also sitting, and this has to be applied to the constraint as well. And that will not be linear, right, in most cases. Your constraint might be a fluid structure interaction problem, it might be a Navier-Stokes equation, it might be a hyperelastic material, not linear. So this will not work in that case. X is not fixed, X is random. Property is fixed throughout. No, always fixed. How? Manufacturing is coming in D. X is the material property. So let me come to this. I have taken a steel sample, the randomness in the elastic modulus. Now whether I make that steel sample as 2 mm or 20 mm, will the elastic modulus change? It is still random, but the randomness will not change because depending on what is the thickness. So when you are saying manufacturing uncertainty, that is in D, not in X. And even when it is in D, we will decompose it in terms of mean and consider the other term to be 0 mean and something like that, and that will be constant. You are right, it can change. It can change, but not in the design stage. This is design. It can change during the deployment. After it has deployed, over time it degrades. Elastic modulus degrades because of environmental effect, because of fatigue and all those things. But that is after you have designed it and deployed it. And that happens over a period in a time scale of years. Corrosion, for example, time scale is in years. So that is not design. This is at the design stage you are doing, but the design stage that will not come. It will come in the health monitoring stage, in the preventive maintenance optimization stage, or predictive maintenance optimization to be more specific, and other things.
If the properties are independent of E, then we can.
In most cases, that will be the case. Give me one example. Example. Think about it and come up with an example. One example I gave you already, that D itself is random, but that you will decouple and make it like that. That's why I always said D is equal to D bar plus D tilde. D tilde is a random, but D bar is constant, and that will go there. So that is then done.
If you're making something temperature based, property will change.
temperature statistics will come during the design stage itself. There is an example where x can change, but that will not change as a function of d, but you are not able to come up with that example. Time dependent reliability, right? The property changes with time, but it does not change with d. You know the property is temperature, it changes with temperature, and temperature changes with time, but temperature will not change based on d. So it's not about whether it changes or not with time, it's about whether it changes as a function of d or not, right? Okay, I'll take 5 more minutes, although this was not working. I'm almost at time, but I'll take 5 more minutes. So this is not perfect, as you can understand. So what people have now, the obvious way to do it is that why should I do it? Why not I build a surrogate model for C, D, x? You can think of building it as C, D, x surrogate model, but then if x is very high dimensional, D, and then it becomes problematic in the sensitivity. So one of the ways is that treat it as a stochastic simulator and build a surrogate model for stochastic simulator. What is a stochastic simulator? Stochastic simulator is something where every time you run, even if the parameter is same, it gives separate result, different result. Now you can consider D to be the parameter, X to be the stochasticity. So it becomes a stochastic simulator. For a given D, you run it many times, you get different results, C, because X is random. So then that becomes a stochastic simulator. For each D, you can generate different C. For a given D, different C's will come, let's say like this. Second D, different C. So now build a stochastic simulator between those, so that when you give D, the stochastic simulator will give you realizations for a fixed D. Using those realizations, find out the mean and standard deviation. This part I am telling very briefly because this is not in the syllabus, but I am particularly addressing him because it is his project. The course project is on stochastic simulator, so it is particularly for you. No, stochastic simulator is a simulator. You build surrogate model for a stochastic simulator. Molecular dynamics is a stochastic simulator. You run it every time, you get different result, you take the mean, right? So any system defined by stochastic differential equation, or SDE, is a stochastic simulator. The idea is but the stochastic simulators are expensive actually. The idea is to build surrogate for stochastic simulator. And in this case, you consider the input to be D, output to be C, but C it's not a unique one-to-one mapping. For a given D, you will have many C's. So that's why you call it a surrogate model for stochastic simulator. So that's what you can do. If you are interested, read about it. Obviously it's not in the syllabus, as I said. Stochastic. But because of some randomness, in this case that randomness X you know, but in some cases you might not even know what is the source of random. But with this stochastic simulator setting, you can reduce the dimensionality. Input dimension is D dimension, the dimension of D. Output is C. The X, which might be 1000 dimensional, is now out of the picture, right? So stochastic simulator is expensive, but surrogate model is not expensive. So that's why you need a surrogate model for stochastic simulator. So in that sense, right? So yeah, so you can build a stochastic simulator or surrogate model considering this as a stochastic simulator, and use that at each iteration to compute this mean and standard deviation, and you can generate D in the upper limit and lower limit, you know that. So do a space filling kind of algorithm and then train it. No, you don't need to, because you have to read about stochastic surrogate model first. So stochastic surrogate model is like a generative model. Now you'll understand. In generative model, there is a Z that goes as input. So here also there is a Z that goes as input. So there is a Z that will go as input, and along with that there is a D that will go as input in this case. So that Z, because it is going as input, even for a given D, you are getting samples. What trajectory? There is no time.
Means they knew that if you feed it and it will try to regenerate it. It knew that you should go in this path. In this case, we know that
In this case, it will learn the probability distribution, right? It will try to learn the probability of C given D. That's what you care about.
in this thing, surrogate model,
Surrogate model without training. Do you know any surrogate model that can work without training? You don't need to know. You don't need to know. That's the whole point. You don't need to know. You read about stochastic simulator. Why are you expecting I'll give you all the answers when you are asking? You could also do some homework and come to me before asking question, right? Do you read it? I've given you the keyword. Go and read it, right? Anyways, they are working on that, so he will know what is a stochastic surrogate model for stochastic simulator. There are papers. Go and read it. Okay. Okay. Thank you. So RDO is done. Okay. Bye.